Good afternoon, and welcome to the Music and Technology Seminar at Carnegie Mellon. Our guest today is Roger Dannenberg, an internationally known composer, performer, researcher, and inventor of music-related and music interactive software. Among his best-known contributions to music and technology are the software that was made into smart music and the digital audio workstation Audacity, which has been downloaded more than 300 million times. Making it the most downloaded audio software in modern history. Please welcome Roger Dannenberg to the Music and Technology Seminar at Carnegie
Mellon. All right, thanks. Zoom is suppressing everybody's hand claps, but I see some hands. Thank you. And thank you, Ricardo. I guess, can somebody tell me if you can hear me okay?
Yeah, we can hear you.
Okay, great. So I want to talk about a project that's actually been going on for a while, but it's a software project called Arco. Let me just switch to slides and I'll tell you more. So take a second to fire up here. Yeah, okay. Good. Whoops. Yeah, okay, so Arco is a sound synthesis framework for programming and creating interactive audio, real-time audio processing. And it works with O2, which is a kind of communication framework that underlies Arco, and you'll see how that works. So you might ask, who needs another synthesizer? Like, what's the point of this project? And one driving force is that synthesizers have become complex with lots and lots of functions in programming systems like Csound and Nyquist. They have big interfaces like digital audio workstations and synthesizer apps. And also they tend to come with language systems like graphical user interface or other baggage like language interpreters in Max and PD and SuperCollider and Nyquist. And so one goal of Arco is to kind of modularize things and produce something that's kind of bare bones that you can use as a library or a small server, or even run it in an embedded microcontroller. So I'm going to show you, talk about some of the main aspects of Arco and how it works. And then I'm going to try to do several demos, which are a bit of a challenge with in the first place, and Zoom makes it a little trickier, but we'll see if everything works. And so Arco design is modular, as are almost all sound processing software systems. So it should be familiar if you've worked with Csound or Max or many other audio programming systems. Arco uses dynamic patching, meaning at runtime you can reconnect, disconnect, connect, repatch connections between signal processors. Sometimes that's very useful for switching smoothly from one scenario to another one, and without trying to compute everything at once. The sort of standard module in Arco, like in many systems, is called a unit generator, and unit generators kind of all have this form. They take one or more signal inputs. They produce a signal output. They have control messages can come in to change parameters, things like reverb time and filter cutoff and oscillator frequency. And they can also generate messages out. So you'll see some unit generators that are used not so much for audio effects or audio generation, but for audio analysis. So they, might measure frequency or estimate chords and send that information out through messages. Arco is designed to be very low latency. It runs in a separate thread that's dedicated to audio processing. And that poses a lot of interesting software construction problems because if you can't sort of freely mix the hard real-time audio processing with, let's say, a graphical user interface that's doing expensive screen redraws. And these two sorts of processes have to communicate. And so Arco's solution is to communicate through shared memory using some lock-free memory management and O2 for communications. I don't want to go too much into detail, but I'm happy to talk about it with questions later. Another design goal of Arco is don't reinvent the wheel. I've worked on a number of music processing frameworks, and it's always frustrating because every framework kind of has a slightly different basis and like the core way in which unit generators are represented and interconnected. And that often means that you have to sort of rewrite everything from scratch, filters, oscillators, physical models, reverbs, synthesizers, tube amps, everything you need implemented, you have to do it all over again. And to avoid that, this time, Arco is compatible with Faust, which is another framework that has a big library, lots of effects and basic audio processing, different filters, as well as some high-level things like synthesizer emulators. And they're all written in Faust, and Arco has automatic translation to sort of extract all of the core processing algorithms out of Faust implementations and put them directly into Arco, so we don't have to rewrite all of that basic stuff. To be efficient, Arco does block-based processing, which means that instead of putting one sample into a unit generator and then taking one sample out and passing it to the next one, processing one sample, and so on, we do things a block at a time. Like we pass in, by default, the block size is 32. So you put in 32 samples, you process all 32, take the output and then pass that on. That's pretty common in other, many or most audio processing systems. And it basically reduces the overhead of getting into and out of unit generators. That's reduced by a factor of 32 or whatever the block size is. So there's also support for multiple channels in Arco. So some systems, like notably Max MSP, you can route signals around, but they're one channel of audio, and I found it really convenient in experience with Nyquist, for example, to have a representation for multi-channel signals. So you put a multi-channel signal into a filter, and the filter just sort of automatically knows to filter each input channel with the same filter design and produce that same number of output channels, just running multiple copies of the filter in parallel. And so Arco kind of automatically, every unit generator by default will sort of run copies of itself on every input channel. But at the same time, you can mix and match. So you can have a channel applying, you can apply a filter to a 4-channel signal, but only control it with one control channel, and that one control will sort of be expanded into 4 automatically. So let me tell you a little about O2. O2 is a communication system designed for music especially, and it's a message passing protocol. So the messages look like this. They have, there's a length field and a flag field we can sort of ignore. And then there's an address. So that's an important thing, that you send messages to addresses, where the first one is, you can think of as being a process identifier. It tells you, sort of what machine you're going to send it to, or what process. And then the rest of the address is just a hierarchical namespace. You can sort of name things anything you want. Usually the last node is the name of a function or a method that gets invoked when the message is received. And the messages have any number of data elements that are described by a little type string. So this means 2 integers and a float. So in this is a message you would send an O2 to Arco to set the frequency of a sign. So it's pretty intuitive. And how do you do that? Well, the I is the identifier for the particular sign unit generator. The second integer is what channel do you want to change, and the third one, the float, is the frequency that you want to set the oscillator to. Again, there's a shared memory interface, so we send these messages from some control process into Arco. And let me skip a little bit. Yeah, so Arco can be running in a separate process, or it can be linked as a library. And one of the features of O2 is it's able to sort of find the Arco process, or whatever name you put here, whether it's on a network or local to the machine, or even in shared memory. So it's very flexible for interconnecting things. So here's, for example, we can run Arco as a standalone server, in which case the main thread does nothing except keep the O2 library processing messages. And when a message comes in, it gets passed into Arco. You can also run Arco as a library, so it's linked into one. It's just linked into it's part of one monolithic program that includes a client application that's sending the messages, and Arco that's doing the signal processing. Okay, so let's see if we can make Arco run, and I'll show you a few things we've done. So I'm going to stop sharing here. Yeah, this should run. Oops, and we're running. Let's see. Okay, I think this is wrong, because I think I need to get the Zoom audio device. So I'm going to reset. Oh, and we're running. I don't know why this is happening. And I want my microphone input as the input. So let's close and reopen audio. So someone, let me see if I can get Zoom visible. So somebody tell me if you can hear well, let me see if I can hear a tone. Oh, I don't hear a tone either. Let's see. Oh, maybe. Oh, I thought, let me see if I shared sound. Yeah. And let's turn on, look for audio settings. Sorry about this. I worked so hard to make everything go smoothly and tested everything, but somehow there's always room for error. Yeah, here we go. Okay, I can see audio from the mic. And I'm getting speaker output. I mean, I'm I'm getting Zoom output into my headphones. So what could be wrong? Let's try this one. And oh, maybe that's. Did other people hear that?
Yes.
We did,
Oh,
but it
oh.
sounded like it was kind of coming through the microphone, maybe, unless.
Oh, okay. Let me move the headphone. These are open headphones, so let's.
Yeah, 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 yeah.
Okay, I mean that should be a pretty clear test tone, but I guess you're not.
I mean, yeah, it's the further away you move, the uh the softer it gets. So
Okay, so let me do this. Okay, I'm just gonna quit and restart. And oh wait, maybe I'm not sure. Okay, let's do this. We're gonna share screen. Now I'm gonna start. And try this again.
yep, there we go.
Okay, good. I think, well, who knows? Okay, so this is, yeah, so this is kind of a test program. So every time we implement something in Arco, we kind of throw it into the test so we can turn it on and off and just exercise it. So there's a few things I can show you. Of course, the test tone was great, and this is a little sequence made with some simple instruments that are created in Arco. So it's dynamically creating instruments, playing them, and yeah, let me just play a little bit. Okay, and then let's see what else is interesting. So we have some granular synthesis code, and I'm going to turn the mic down a little bit and then try to play with this. Yeah, okay. So this is some a granular synthesis processor. We have variation. So that's fun. There's also a phase vocoder test. Phase vocoder. I can turn this up a little bit. Okay, yeah, this is one channel, but it's obviously doing pitch shifting, and there's a little bit of latency because it's using spectral frames and it's hard to talk. FFT size is about 2K here, so that's most of the delay. Let's turn this off, and we have a yin algorithm, which is a pitch estimation. And if I grab my trumpet here, so we can make a steady pitch. can't see it and play at the same time. So I'm a little sharp, but I think you could, I hope you could see those numbers. Um, let's see, we have a, oh, let's see, what else should I look at? Um, let's just run down to some of the analysis code we've been working on is, this is chord detection. I should have gotten a keyboard out, so I can't play any chords. But I think if I just play some notes, let's just play a B flat. So it's kind of saying it's a B flat major, and but it recognizes major and minor chords and does a reasonable job pretty fast. We have some spectral centroid estimator. It's another feature, and a spectral roll-off feature. There's also some onset detection that's based on spectral flux. So you can, it's probably hard to see, but it's, picking up onsets from my voice and blinking that little light when it detects an onset. Yeah, okay, so that's a quick test or run through. I'm trying to think, let's see. Oh yeah, so I want to go back and switch to, I should tell you about the control language. Still good? Okay. At the lowest level, we control Arco with through O2 messages. So this is an example. You probably would never actually write this, but it's useful to kind of understand the mechanisms. If you wanted to play a sine tone, you would construct a constant unit generator, which is a thing. It just outputs 440 in this case, and we're giving it number 10. Every unit generator has to have an integer to identifier, so we can mention it later in messages. So we create 440 at ID 10. We create another constant of 0.1 at ID 11, and then we create a new sine unit generator. It's going to be ID 12. It's going to have one channel, and the frequency will be given by 10, which is 440, and the amplitude will be given by 11, which has the value 0.1. The reason, well, these could also be, these don't have to be constants. That's why we have this little bit of indirection here. It could be a low frequency oscillator controlling the oscillator frequency, or something much more complicated. Anyway, we create the sine, and now we have the sine is ID 12, and to play it, there's a sum unit generator that just adds all its inputs, and it's the one with ID 3 is connected to the audio output. So we just basically say sum this sinusoid into the sum node or the sum generator 3, and we'll hear it. Later, when we want to get rid of it, we send a remove message to the sum 3, telling it remove unit generator 12, and it will be removed and memory will be freed up. And oh, sorry, the memory won't be freed because we still have the oscillator is still there. But if we call Arco free of 10, 11, and 12, then there will be no more references to these unit generators, and they'll all get freed, so we can reuse the memory. So that's kind of what the low level. That's what's happening to control the Arco process. But then to make it kind of more usable, we have a high-level scripting language. Currently Serpent, we're working on porting this to Python, that you would write something like this. You just say, I want a sine with these parameters, and after you create it, play it, and we're going to save that into sine1 so that we can reference it in the future. And then in the future, if we want to get rid of it, because otherwise it'll just run forever, we can call mute, which makes it silent, and we can get rid of our reference to sine1 by just assigning any other value to it, like nil. And then the garbage collector in Serpent will automatically free everything associated with sine1. So that's kind of what the language looks like. One thing I've been doing with Arco is using it to kind of recreate some interactive pieces that I wrote. And interestingly, just this morning, I got email from a trumpet player that wanted to play this old piece, Resound, and I have an old implementation. It runs, but rather than maintaining that, I think it's cleaner and easier to move everything into Arco. So that's what I'm doing. And I want to play a little, one movement of Resound for you, just so you can hear it. And we'll have to try to get things working again. But I think all right, I'm going to stop sharing and check one thing. Yeah, I'm going to switch that and quit that. Pull this up. Okay, so let's, I'm going to do another quick sound check here because I don't trust anything. Let's see. Oh, that's not what I wanted. Okay.
You can tell Roger his voice is great.
Yeah, let's. I'm not sharing. Okay, wait a minute. Okay. Turn all of that on. Run it again. Okay, now let's see what happens. All right, are you getting some processed voice?
Yep, I hear that.
Okay, good. So I'll turn this off, try to reconfigure for trumpet, and I'll play a little of this. Oh, and then I forgot one other piece of introduction is this piece is has 7 movements, and each movement it has a set of controls. And what I was planning to do was operate the controls with a foot switch, which is possible, but due to some technical difficulties, it's not working at the moment. So I'm going to manually have to sort of cycle through a bunch of settings that you see. We're going to play movement 6 called Ripples in Time. And so you're going to hear a lot of pauses in the music as I run over and click on the next preset here. So bear with me, and here we go after a little reset. Okay. Um, Back to voice audio. Okay, so that was Ripples in Time from Resound, and I have this piece and a flute piece that's both have been recorded, and some other pieces. So still trying to get performances and make it easier for people to set up and play these things. Oh, all right. So the next thing I want to demonstrate is the use of O2 to interconnect with browsers, because there's all kinds of interesting software that runs in browsers, including you can use browsers to build control panels, to render graphical output. I mean, you can take output from Arco, like the chord pitch detection, chord estimation, spectral centroid, feed all these into a p5.js or other graphics program that runs in browsers. And you can also, in this case, we're using camera input with some object recognition software that is very convenient, easy to run in a browser, and we're feeding that. Here's the diagram. We feed that through O2 messages.
Roger, you're not sharing your screen.
Oh, thanks. Okay. And yeah.
Yeah, there we go.
Okay. Yeah. So we send O2 messages from the over WebSockets from the browser into O2. Those get sort of analyzed by some control software, kind of mapped from the screen parameters into sound parameters, and those are fed into a little synthesizer, which is just sine wave oscillators and a filter. And but the cool thing is the interaction. So let's see if I can get this thing going. All right, this is not going to rely on microphone, but I guess, oh yeah, so this, what are we doing? I have to go back and quit Resound. And then I'm going to go back to the first thing. Run this. No, I'm sorry. Wrong thing. Let's, yeah, we're supposed to be running hand track. Pull this down here. Okay. So that's running, but I also need a browser window. See if this works. Turn on the camera. Okay, so I'm gonna drag this browser window down here so you can see it. So here's, I think you're seeing my face with a box around it, and good. Okay, and you see these. It's showing us the messages that are being sent in kind of the raw form, just to confirm. So that all looks good. I'm going to turn sound on. And we have volume. This gets softer and louder. Okay, so that's the hand track to Arco demo. I heard somebody laugh, so I guess you're hearing the sound okay.
Yeah.
Good, okay. Yeah, it's fun. Um, okay, and okay, oh, let's see. What's next? Oh, yeah, so let's talk about control and processing in Python. So one of the goals and sort of the teaser in the title of this my talk was AI and machine learning. And one of the things I've thought would be really interesting to do with Arco, and we're slowly getting there, is because of O2 and the ability to send messages out of the strict real-time audio processing world into some other world like browser world, or could also be PyTorch and machine learning world. So my thought was we can use things like chord analysis and pitch analysis and spectral centroid and all these features we can extract from audio. We could send them over O2 messages to a kind of machine learning system, which I certainly don't want to put inside Arco. The idea is let's go for modularity and connect things with O2. So we'll send the analysis data over to something running Python, which is what people use these days for programming, for doing machine learning. And we do processing and inference on that in Python and PyTorch. And then we send the messages back. And if you don't have enough processor in one machine, well, Arco scales over local area networks, and so you could run this on a couple of machines quite easily. So it's just a very flexible system. So moving in that direction, I'm gonna we gotta kill hand track. I'm going to go back to the original, no, not this one. This one. I want to go back to this original test program because one of the tests that we didn't get to was O2 audio test. So O2 audio is a unit generator that sends audio over O2 and also receives audio over O2. And so I believe with that running, let me pull another screen over here. We can just say whoops, loop back. If I could just type. Yeah, let's see what happens here. And maybe I should turn the level down a little bit. Yeah, there we go. Okay, so what's happening? I mean, this is super boring, but we're just creating a sine wave for test purposes because we ought to be able to hear any kind of dropouts or distortions from a pure tone pretty easily. We're sending a pure tone over O2, and if it finds a process to connect up to, which is this Python process, it will send the messages. And the process is receiving the messages and just turning them around and sending them straight back. And so the goal, and then we're playing what comes back. So the goal is if we hear a continuous smooth sine tone with no dropouts and no distortion, that means we have full bidirectional audio communication with another process, which is what we're hearing. I tried with different buffer sizes. I mean, there is some buffering because once you go outside the audio process, you can't get extremely low latency or real dependable processing, and so you make up for that by using cues and buffers, so that if if the incoming audio is a little bit late, you just pull samples out of your queue for 10 or 20 milliseconds, and hopefully the incoming messages will catch up. So that's That's one little demo. And the cool thing is, I mean, in addition to all of that, it's using O2, and the way it makes connections is pretty powerful. So it sort of knows when the service has been dropped, and it will reconnect to a service if it comes back. So you know, I just restarted the process, didn't have to do anything on the Arco side, and O2 just sort of automatically start, you know, started sending messages again. I can even change the program on this side. I wrote a real simple thing to do some audio processing on the Python side. So what this does is adds amplitude modulation to the incoming signal. I mean, which is very simple and very boring, but you probably don't want to do a whole lot of sample by sample signal processing in Python anyway. And so, you know, the point is if the signal comes back and it's a pure tone, but it's amplitude modulated, then things are working. So we'll let it fire up and get connected. And so there we go, a nice amplitude modulated sine wave. And so we're actually doing the amplitude modulation in Python. And we, you know, we're getting some statistics about what's happening in Python with timing. Okay, so that's that. Let's talk about, oh, all right, I'm gonna switch back to, oh, I was already in, I meant to switch that to the good audio mode, but anyway, I guess you heard it. Okay, so are we, yeah, okay. So what's next? One goal of Arco is targeting embedded computers. That was kind of an inspiration to seeing people really struggle to do things like run a PD library on a Raspberry Pi. I think Arco is more suitable, so that could be fun. As I said, we're working on a full kind of implementation of the scripting language in Python, because I think there's a lot more. There's certainly a lot more Python programmers than there are Serpent programmers. Serpent is my scripting language that's running in Arco right now. I have some other compositions to port from another framework into Arco. And we haven't done a whole lot of performance measurements, so we probably need to think about optimization and performance, although it's, you know, it's playing pieces and seems to function really well. So just to wrap up, Arco is ready for experimentation. If you'd like to play with it, I'm working with some other students, and you know, be happy to share. It's especially suited as a synthesis add-on for any application that needs sound output. You know, maybe games, but game audio is already has some frameworks, and it's a little kind of specialized towards spatialization. It could be a really nice library for embedded computers because it's very customizable and kind of minimal. And also, as I said, we want to connect AI and machine learning programs to audio I/O for processing and control. And so we have some experiments to do there. So that's, let me stop there, and I guess we have a few minutes for questions.
I had a quick question. Can you hear me?
Yeah.
All right, perfect. First of all, it's like phenomenal work. It's like really impressive to see like that you're able to, you know, get all of this running. One question I had is, you mentioned that O2 kind of has this structure of you know, the communication structure, like sending specific messages uh, to specific modules of some sort. And then you also later mentioned that you're sending um, just pure audio over O2.
Yeah.
So how does that is it like a whole separate part of O2 or
Oh, yeah, actually, okay, so um, this O2 audio object, when you create it, you tell it what you want to connect to, like where to send the messages. So that's the address string, and then the value that you send is a special value that exists in or special type that exists in O2 called a blob, which is uh, like an acronym for something, binary large object or something. And so a blob is just a sort of an untyped, well, its type is string of bytes.
right?
And you could put anything in there. And then so on the receiving end, we have to, in Python, we have to take the, the, the bytes out of the blob, convert them in I think I'm sending 16-bit samples, but you know, yeah, we're actually sending them in, proper network byte order. So when they arrive in Python, you have to, unpack them, convert from network byte order to local machine byte order, and then convert that into an array in Python that you can process.
All right, yeah, yeah, that makes sense.
So it's pretty simple. I mean, it's just, basically we send blobs of samples. The sample, like the buffer size that we're using is, I think I ended up with either 256 or 512, because if you send 32, uh, O2 is willing to do it, but the message rate is so high that I mean they're getting sent in this case over TCP IP, but locally within the machine, but still that message rate was not working. So uh,
Yeah, that's a lot of messages to be sending 32 samples.
yeah, so 32. I mean the block rate is over a little over a kilohertz, so a message every, you certainly cannot do that over Wi-Fi. Um, and so it's just, it's more efficient to send bigger packages of fewer messages.
Makes sense. Yeah.
So Roger, is there any way to have interactive musician, for example, let's say you had someone who plays jazz guitar, to use this to play a piece that would respond and play back certain things and interact with the performer?
Oh yeah, sure. I mean, just like, the trumpet thing that oh, well, okay. So, well, yeah, to finish, the trumpet thing I just played was, uh, you know, all, all of the sounds were coming from the mic, from the trumpet through the mic, and it's manipulating these sounds. If you're talking about, um, y- you know, interaction at a higher level, like I mean, you said a jazz guitar, so you're thinking about, jamming or trading licks or something like that, then yeah, I mean, maybe that's one application for the some of the machine learning stuff is we can analyze pitch and onsets and brightness even of the or chords of the guitar and send that information to some other program that's been trained in some way and with machine learning, and then it could formulate some kind of response and send it back, and then we could synthesize that response from, I mean, there's a MIDI synthesizer built into Arco with guitar sounds, or you could do a physical model for strings, or any number of audio synthesis algorithms could be used. So, in principle, yeah. I haven't myself. I'm just trying to think. I mean, yeah, a lot of my pieces are kind of related to that, but um, yeah, I guess I could say this just over the history of interactive computer music systems, um, there's been a tendency towards kind of interaction and improvisation in this experimental music that is not traditional kind of rhythmic and harmonic um, interaction like trading licks in a jam session or something. And the reason for that is partly that composers are more interested in more experimental stuff, and so it tends to sound more like avant-garde music or free jazz than something conventional. And the other reason is just that machines are still struggling to do things that musicians do easily, like beat tracking and anticipating chords and forming phrases and structure. Um, those kinds of high-level music abstractions are pretty tough for machines. And so, at least historically, um, people have come up with, I think beautiful music and great stuff, but not sounding like conventional music because just even playing on the beat is a challenge for a computer. But maybe with deep learning and machine learning advances, people will turn back to doing, some more rhythmic, harmonic, melodic creation as improvisation.
Oh, I have a question. Roger, I really
Yeah.
enjoyed the piece that you played on the trumpet. And I noticed that you have a lot of different presets from 1 to maybe 7 or 8. So if a musician wants to make their own presets, what's the current workflow like? Do they need to?
Oh, yeah. Let me. Uh, I think I can quickly show you kind of what that looks like under the hood. Um, yeah, let's try this. So the quick answer is yeah, you can, like, none of that stuff is built in. You can sort of do anything you want. Uh, let's see. Yeah. Okay. So oh, good. So this is pretty. I wasn't quite sure what the code was going to look like or what we'd find, but this is pretty clear. So we have this uh, shift delay unit generator that I did create, and it's defined someone else. But what it does is it takes the delay between the period of the delays, which is a quarter of a second, and it you pass in a bunch of frequency ratios. So this means -2 is down a whole step, -5 is down a fourth, and then a fifth, and an octave, and a major ninth. So these are the intervals, and they're all equally spaced in this piece by a quarter second. Boom, 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 and and these are the preset numbers. So when we shift from the first thing to the second preset, we're just changing the intervals, and so it's all constructed. I mean, you could sort of make it do anything that you want.
Got it. So it's Python scripting.
Yeah, I'm sorry, say that again.
Oh, so I said I got it. So it's basically Python scripting if someone needs to modify it.
Yeah, yeah, that's right. And the code I showed you was actually Serpent, so but it's very similar to Python, so I think it's pretty easy to use. But before long, we're going to have an actual Serpent implementation for people that really want to program in Serpent.
So Roger, if they were a brilliant music and technology student here at CMU who wanted to use this as a framework to do other work. Is that possible? Do you make code available or?
Oh, sure. It's all open source, and I've been working with students, and really like the biggest barrier until hopefully until recently, like I think we're beyond it, has been that this Arco with the Serpent language integrates a lot of stuff. There's O2, there's MIDI input, there's the audio IO library, there's the graphical interface, that built all the control panels, which is another big subsystem, and getting all of that stuff to installed on your computer and getting it to compile and run has been a real challenge. But we now have a script that will just build. You sort of just download one file and run the script, and it takes about 15 minutes to import all the stuff and build it, but it seems to be working. So yeah, I'd be happy if anyone wants to try it. It runs almost. I mean, I would encourage anyone with a Mac, if you have Windows, the whole build process is more complicated, unfortunately, and it's kind of hard to script stuff for Windows. So we're that's a little bit harder to get into. But yeah, I'd be happy to work with anybody that wants to try it out.
Hey, Roger, I have a question.
Yeah.
I'm wondering what's happening when the program is identifying a single note, like as you did with your trumpet, when you play the B flat. Immediately I think about the overtone series, and I think about how I mean, maybe I'm missing something, but maybe like why I wouldn't consider it as a chord, as a B flat 7 chord. I noticed that it registered it as a B flat major 7.
Oh yeah. So yeah, it's a good question. So the chord recognition algorithm, yeah, does sort of distill the spectrum down to pitch classes. It's called a chromogram. It's basically a vector of 12 weights that tell you, how much energy around C and how much energy around C sharp and D and E flat and E and so on. What was the relative amount of energy that it saw? And then it has a bunch of templates for chords, and it basically searches all the templates to see which one has the highest correlation with the actual chromogram that you're reading. And so yeah, I mean, there's definitely the seventh harmonic, and it's going to create raise the weight on the minor seventh in the chromogram. But I think it gets just overwhelmed by the fundamental and the fifth probably, and so overall, I guess it was just a better match to the B flat major than a B flat major 7.
Thank you.
Any other questions? Anyone from online? We have total silence here in Los Angeles. Okay, here's one. Go ahead.
How do you have it detecting the onsets?
Oh, yeah, we're using, I'm trying to think of the library name. There was a PhD thesis that implemented and compared a whole lot of musical onset algorithms. I mean, you can imagine a simple way to detect onsets is just look for peaks in the amplitude. For some instruments that works, and some things that works great, but if you think of like a violin playing in a room with reverb, the amplitude's never going to go down much, but the pitch might change or the phase might change when you reverse bow direction or something. And so I think the winning algorithm is basically a spectral flux, which means you look at both the phase and the amplitude of every bin in a spectrogram. Spectrum, FFT, from one FT to the next, and you kind of sum up all of the changes, and you get an overall difference in both phase and magnitude. And then you have to search for peak detections. And this guy also analyzed a whole bunch of algorithms, and I think it's using a what would it be, a linear predictive coding, trying to predict the next sample, and then it looks at the error in the linear predictive coder. When the error is high, it means there was a big change, and then it reports an onset. But that, detecting peak detection is there's hundreds of papers in the literature about different approaches for something as simple sounding as detecting peaks, because you don't know how loud the overall sound is. You don't, the signal may have a lot of variance, so it looks like it has a lot of peaks, but that's just sort of normal. But anyway, we use somebody else's algorithm because they tested a whole bunch of stuff, and this is what worked the best. And it's basically, I believe it's kind of spectral difference algorithm.
Any other questions?
I had a quick question. We can probably talk about it offline if it gets, too deep in the weeds. But I was just wondering what you're actually using to write audio, like sending audio output into, the system.
Oh yeah. So we're using the port audio library because it's pretty mature. It's been used for a long time. We use it in Audacity. Lots of people use it. Getting the big advantage is port audio will send audio. I mean, it's one interface for your code, but it can drive audio output to the Mac and to Windows and to Linux and multiple different audio systems like Jack, and so and each of these systems has plenty of quirks, and
Right.
port audio has sort of seen everything and there's like so many special cases, and it's really comes down to that these audio systems are generally very poorly designed, I think. And so you need help from something like port audio.
Right, and they're not meant to be they're not designed to be compatible with a bunch of different things or anything.
Yeah,
Uh,
it's compatibility, and it's also just, well, I think maybe the people that build these interfaces are so concerned about efficiency that they don't provide very good abstractions. I mean, that would be the excuse. If I wanted to be cruel, I could say, well, they're just lazy. They don't know how to design a clean API or a clean model, and they don't want to take the time to implement, to handle all the weird exceptions and special cases. So they just pass all the work on to port audio, but fortunately it stops there.
yeah. All right.
Okay, Roger, thank you so much for doing this once again.
Yeah, thank you.
Thank you.
See you again soon.
Great to see you guys. If anyone has any other questions, or email me anytime.